Hi everyone. So we are continuing our discussion of functions here in Chapter 2. In Chapter 2 so far we have discussed quadratic, linear, and exponential functions. And the second half of this chapter is focused on this idea of modeling. So modeling is just a fancy word for representing real life situations. In other words, these are going to be your story problems. These are going to be your word problems. And we're going to be given a scenario and we're going to model it using a function of some kind. So there's kind of a mismatch of examples here because they all just have to do with, different types of functions and how we can write equations to represent these situations. So let's just dive right in. So example 1 is talking about a car depreciating at a rate of 12% per year. Anytime you're working with a percentage, we're going to be doing some form of multiplication here, right? Because that's how you apply a percentage, is with multiplication. Now, I said some sort of multiplication, not necessarily the 12%, because the 12% is what we're losing, right? If we're depreciating by 12%, I don't really care about the 12%. I care about what I get to keep, okay? And so if I'm losing 12%, this is one of the things that people miss on these problems all the time, is I want to figure out what percentage do I get to keep. So 100 minus 12 is 88%. That's what I'm using to build an exponential function here. So it says, write a function to model the value of a car originally purchased for $25,000. Okay, that $25,000, that's my initial value. And this 88%, that's going to become my B value. That's going to become my growth factor. So my function is going to look something like this. A, we said, was 25,000. My growth factor, 88% in decimal form is 0.88. And then we're doing that every single year, so we're going to the power of x. I want you to think about this. This B value is smaller than 1, right? Multiplying by 0.88, that's smaller than 1. So that is going to make this value decrease or depreciate. And then, of course, I could ask you questions about okay, now find the value after 10 years or something like that. But in this one, that's all it wanted was the function. Okay, example 2 is another exponential function. We're looking at a population growth, okay? U.S. population in 2024 was 340 million people and is growing. I'm going to highlight that word. We are growing at 0.98% per year for the near future. So this is our A value. That's what we're starting at. This is going to become our B value, but just like in the last question where we were losing value, this time if we want to grow, we need to add this 0.98% to what we already have. And what we already have is 100%. So I'm going to take 100% and I'm going to add 0.98% to it. So that's 100.98%. By the way, if you need to do this in a calculator, there's no shame in that. Sometimes with all those zeros, it gets confusing. If you need to do it so that you can see this number in front of your face, I encourage you to do that. And then I'm going to move my decimal point over twice because that's how we deal with percentages. And so I'm going to get that my B value is 1.0098. So these are the two numbers that I'm going to use to write my formula here. My U.S. population, we can use a Y or a P or whatever, but this is my population. 340 million people. I'm going to just use 340 and then specify that my answer here will be in millions. And then here's my growth factor, 1.0098 to the power of x. Now this is growth because I'm multiplying by something larger than 1. So I know that I've established growth. If I just did the 0.0098, I'd be shrinking because that's smaller than 1. So the 1 is important here to make sure that we're growing. Okay, from the formula, estimate the population in 2050. So this is from 2024 to 2050. Let's figure out how many years that is. I believe it should be 26 years. So we are doing 340 times 1.0098 to the power of 26. Now, I'm going to use a calculator for this. And I know that you probably could have just gone straight to your calculator with that and gotten that answer. It's really important that in things like notes or homework assignments or whatever, you write down your setup like this so that you remember where this came from. This is how you practice, is by writing these things down. It just organizes your thinking a little bit. 1.0098. Now I am expecting this to grow, right? So it should be higher than 340. It shouldn't be like astronomically higher than 340 because this is not a very big percentage. So let's see where we're at. Well, that sounds about right to me. So I would say 438 million people. That's my estimate. Okay. Next example is another form of exponential modeling. This is a concept specifically known as half-life. Let's see if I've got another color here. You may need to write this definition down, and you may have worked with half-life before, maybe in chemistry or something like that. But half-life is the amount of time it takes for a specific quantity to decay in half. This happens a lot with radioactive material, that it slowly deteriorates, and over time it will, reach half of its original value, but it never goes away completely. Okay, that's the idea here. So in this first example, a certain substance has a half-life of 24 years if a sample of 80 grams is being observed, and then we'll work through the rest of this. So, okay, the 80 grams, that's how much I'm starting with, so that's my A. If we are working with half-life, what's happening to that is it's cutting in half, right? So my B value here is always going to be 1/2 or 0.5. The way we deal with the 24 is as follows. So let's just say that I write my equation and it's y equals 80 times 1/2. Now if I just go to the power of x, that's going to cut in half every single year. That's too fast, right? It needs to take 24 years before it cuts in half one time. So I want to do something up here to my exponent to make it so that I'm taking these years and putting them into groups of 24. And when I finally reach a group of 24, that's when I get to cut in half one time. And so the way that's going to work is we're always going to put this up in the exponent like this. Okay, so this first example, how much will remain in 96 years? This one we actually could have done without writing an equation. We'll definitely need the equation down here. But 96, if you don't know this off the top of your head, is really 24 times 4. Okay, that's 4 sets of 24 years. So every 24 years we're cutting in half. So I could figure this out like this. And if you wanted to use the equation, you could. This is how much I'm starting with. So after 24 years, I would be down to 40. After another 24 years, I would be down to 20. After another 24 years, I'd be down to 10. And after another 24 years, I'd be down to 5 grams. Okay, so altogether, this represents 96 years worth of time that I'm cutting in half every time. So I like to run through that one that way just so that you can really get a concept of what it means to have a half-life, right? This is how long it takes for you to cut in half. So now 50 years. 50 years is not a perfect multiple of 24. Now it's awfully close, right? Because 2 times 24 is 48. So we're expecting it to be probably a little bit less than 20, because this is how much would be left after 48 years, and we're going to go a little farther than that. So we're expecting a number that is a little bit smaller than 20. Let's see what we come up with. So for this, I'm going to use this formula, and I'm going to say we're starting with 80. I'm using a growth factor of 1/2, and then we want 50 years, but we're dividing that by 24 in order to make it so that I'm figuring out how many sets of 24 there are. How many times do I need to cut in half? So in my calculator, 80 times 0.5 or 1/2 to the power of, now depending on your calculator, you might need parentheses around this exponent, but on this style of calculator where it's all kind of typing up there, this is fine. And I get an answer of 18, remember we said it was a little less than 20, so 18.8, we'll say 18.88 ounces. Okay, this next question is easy and hard all at the same time. It's easy because we actually answered that question up here, right? When will I have 5 grams? Well, that was our answer for 96 years. So we already know what our answer should be, right? It should be 96. But what this is actually asking me for is when will this, whoops, get the rest of my equation here, times 1/2 to the power of x over 24, when will this equal 5? Now, to actually solve this, you would need logarithms. And you learned a little bit about logarithms last year, so you could dive in and try it that way. For right now, that's not what I'm expecting you to do. I'm expecting you to graph this. So I would expect you to graph y equals this equation and y equals this equation, and look for when, for what x value does this equal that. Now, I don't have my camera set up in a way that I can easily pull up Desmos for you, but that's what I would do, is I would graph this equation. I would graph the line y equals 5. What I'm going to see is an exponential decay, which is going to look like this, right? And then I would see the line y equals 5 coming across like this. And wherever this point is, that's my x value, okay? So I'm going to kind of skip over that here, but you could do that pretty easily using Desmos. Okay. Next up, I believe this is some linear modeling. Okay. A gym offers 2 membership plans. We can either pay $40 a month, or we can pay $10 a month, but then we have to pay $2.50 each time we actually go to the gym. So we are going to model this, meaning we're going to write equations to represent this for each plan as a function of the number of visits in a month. Okay, so watch how I'm going to do this. I'm going to use a notation that you're going to see, as you move on in math. I'm going to do the cost of plan A, and I'm going to do the cost of plan B. Also, whoops, I meant to do that up here. I realized something was wrong there. Cost of A, cost of B. Because I want to just compare like 1 month's worth of time, right? I'm just going to consider this as being 1 month. Like, we're going to look at both plans for just a single month. And then we could talk about, like, okay, over 5 months or over 10 months, but I mean, really it should be changing by the same amount every month, depending on your number of visits. So I'm going to say the cost of plan A in just 1 month is 40. And the cost of plan B is 10, but I also have to add $2.50 for every visit. So the reason I did that with just doing 1 month is the fact that if I were to put in like the number of months, I'd have more than one variable going on here. And since I want to compare them, I can just look at 1 month at a time. Okay, so if you go 10 times in a month, and again, we're only looking at 1 month here, plan A, still just $40, okay? Plan B, well, I would only have to pay the $10, but then I'd have to pay $2.50 10 times, right? Because I'm doing 10 visits. So $2.50 times 10 is going to give me $25, so this is just going to be $35. And so I would say for 10 visits a month, plan B is still the better one, right? Because it's only $35 as compared to $40. So I'm still lucking out with plan B. So now the question is, what would impact your decision about which of these plans is best for you? Okay, is it always going to be plan B, or is there a time when plan A would be better? Well, I hope that you're thinking about that number of visits, right? Because this is going to make this thing increase. What we would see, again, if we were to graph this thing, is plan A is always $40, no matter what. Always going to be 40, okay? Plan A is going to start down here at $10, but it's going to increase, okay, by 10 each month. So that 10 is essentially the slope of this line. And so there's a break-even point here, right? There's a place where the two are the same, and then after that point, this plan B would end up being more expensive. So I would base my decision on the number of visits and if I wanted to be more specific, I would find the value of this actual point right here and be able to say, like, hey, if I was going to go more than that many times, the $40 is great. If I was going to go less than that many times, this would be better. I want to say, just based on this, because if I added 2 more visits, that would add another $5, and that would make the break-even point. So 12 is this place where they're exactly the same. And so if you were going to go more than 12 times, I would stick with the $40. Okay, finally, a type of quadratic modeling here. So this is just one example of a situation that can be modeled with the quadratic equation. This is Newton's formula, and Newton's formula is a law of physics, okay? And this talks about the path of an object that's been projected into the air somehow. Either it's thrown or it's dropped or whatever. But we're going to be looking at a situation like this. Something gets thrown up in the air and it comes back down. So look at that nice parabola there. That's modeled by this formula right here. Now, I do think it's important for you to kind of understand how this formula works, and I think you're going to learn it in physics class. I'm probably always going to give you the equation all written out here so you can see what I did here, and I'll explain that as we talk through this example. So you don't have to memorize this necessarily, but I think it's important for you to understand it. So, a projectile is shot from a tower 10 feet high. So this is the initial height of the object. That's what we call h sub 0. So that's this. With an upward velocity of 100 feet per second. So this is v sub 0. The other value for you to understand is this value g. So we've talked about h sub 0, we've talked about v sub 0. Now we need g. G is force due to gravity. Okay, this is the force that gravity is exerting. The good news is, as long as you're on planet Earth, gravity is constant. That's a little bit of a lie. It changes based on your altitude a little bit. But for the most part on Earth, we're going to assume that our gravity is always going to be the same. The bad news is it does depend on which way you're measuring it, whether you're measuring in feet or in meters. So this G value is 32 meters per second if you're in, nope, I'm sorry, I did that wrong. It's 32 feet per second, okay, if you're measuring in feet, or it is 9.8 meters per second. So you will always see either a 32 in that equation there, or you will see a 9.8, depending on whether you're in feet or meters. Okay, so in this one, I went ahead and set up the equation for you. You'll see that I put in the 10 and the 100. I put in a 32 because all these measurements are in feet, and this is what this equation simplifies down to. So it says, how long will the projectile be in the air, and what is the object's maximum height? Now again, and maybe I should even switch over and do a new video so that I can do Desmos with you, but let me just sketch a picture here. This is what's happening. It's leaving from a height of 10, that initial height of 10. It's going up in the air, and it's coming back down, okay? So when I say how long will the projectile be in the air, and this is time down here, this is height up the side, what I really want to know is when does this happen, right? That is a root of the quadratic. The the root of the quadratic we find by doing quadratic formula. Okay, we can also just graph it and look on Desmos, but that's what we need to know, is what is the root of this thing. Now, when I find the roots, I'm probably going to find a second negative root, and that's, this value over here. This doesn't really mean anything to us in the context of this problem. But this root we could find with our old friend quadratic formula. What is the object's maximum height? Well, the maximum height is talking about the vertex. Now, what you want to remember about that vertex, the vertex is h comma k. The h is your x value. So the h is really talking about time. And the k is a y value, which is talking about height. The problem with this is that you want to think h represents height, but because h is an x value, this is time and this is height. So this question wants to know what is the maximum height, which means I would look at the vertex, but what I really need is the k value. If the question asked when will it reach the maximum height, then I would need the x value here from the vertex. That's when, and this is how high. Okay? So, like I said, you could solve these by hand. I would love for you to try solving some of them by hand. You could do quadratic formula. You could find the vertex using your h and k magic. Or we could graph this thing on Desmos and just pull those values from there. What I really care about is that you know what you're pulling so that you understand like which piece of the parabola is it that I care about here. Okay, make it make sense to yourself. That's really it for this lesson. Like I said, it's mostly just a bunch of word problems. So if you do have questions on those, we're going to try some of these together in class. But this is really just about how do we apply these functions to real life situations. So hope you have a great day, and I'll be seeing you soon.